In today's video, we're going to finish up our series on equilibria by talking about equilibria that occur when partially soluble salts are put in water. Some of the concepts that we'll discover today will seem familiar to you from your study of equilibrium in general and acid-base equilibrium in particular. I'm going to start out with this quizkin. This is based on a real-life experience of mine. As I was cleaning out our car one day, I found this juice box under my daughter's car seat. And I want you to explain the circled part of the label. So stop the video here and read that label carefully and see if you can explain what they're talking about in that circled section of the label. Well, here's your solution. Citric acid is in this mixture, and it says that provides tartness. Well, tartness is sourness, and sourness is a characteristic of acids. The more acidic something is, the sourer it tastes. And also, potassium citrate is in there, and it says that regulates tartness. So what we've got here is a buffer system inside this high C. So we have citric acid. I don't know what citrate is, so I'm just going to call it H-cit. It's actually a triprotic acid, I think. And that'll be in equilibrium with protons and the citrate ion, whatever citrate ion is. I'm going to call it 1-. It's actually triprotic, but we're going to use the first ionization. Here's the idea. I have some of this present, and I have some of this present in the same mixture, in this beverage. So excess H plus is not allowed to lower the pH because the tartness is regulated by the fact that this citrate ion source from the potassium citrate provides a buffer system. If you take a partially soluble salt, in other words, one that is not considered to be soluble on our solubility rules chart, it actually does dissolve to some extent, but it reaches dynamic equilibrium once the solution is saturated. And even the totally soluble salts do reach dynamic equilibrium at some point. Well, here's what that equilibrium looks like. On the left-hand side, we have our salt. I'm calling it cation for cation and anion generically. And that's a solid. And on the right-hand side, it's dissociated reversibly into a positively charged cation in aqueous solution and a negatively charged anion in aqueous solution. And of course, the stoichiometry is 1-to-1 in this generic thing, but it doesn't have to be. So for example, if I had silver chloride will reach dynamic equilibrium with aqueous silver ions and aqueous chloride ions. PbF2 will reach equilibrium with lead-2 ions and fluoride ions, but the stoichiometry is 1-to-2 here, so 2F- aqueous. The mass action expression for this equilibrium will not include the solid that was on the left-hand side. So K for this reaction is just going to be the product of the aqueous cation and aqueous anion concentrations raised to their coefficients. And it has a special name. It's called the solubility product constant, and the abbreviation is KSP. So KSP is equal to the product of the concentrations of the cation and anion in solution raised to their coefficients. So for our two examples, AgCl, KSP for this is going to be concentration of Ag plus ions times concentration of Cl minus ions. And for the PbF2, well, KSP here is just going to be the concentration of Pb2 plus ions times the concentration of F minus ions, and that would be squared because the coefficient is 2. So here's a problem to help us get comfortable with the idea. 1 liter of water is able to dissolve 2.08 times 10 to the minus third moles of lead-2 fluoride at 25 degrees C. And the question is, what is KSP for lead-2 fluoride? Well, the equilibrium here is PbF2 is in a dynamic equilibrium with Pb2 plus in aqueous solution and 2 F minuses in aqueous solution. Initial concentration. Well, PbF2 is not in our equilibrium expression, so we don't care what its concentration is. And before the dissociation takes place, there are neither Pb2 plus or F minus in the solution. The change? Well, the stoichiometry is -1 plus 1 plus 2 X. But we actually know what X is here. X is the number of moles per liter of PbF2 that will dissolve. And the problem tells us that this is 2.08 times 10 to the negative third. So at equilibrium, we don't care about PbF2, and X is the concentration of Pb2 plus, and 2X is the concentration of F minus. KSP for this salt is going to be concentration of Pb2 plus raised to the 1 power times concentration of F minus squared. So that's 2X, so that's X times 2X squared. And that would be 4X cubed. So it would be 4 times 2.08 times 10 to the negative third cubed. And that works out to 3.60 times 10 to the negative eighth. So that's our KSP value. Just like we saw with buffer systems, there's a common ion effect that can take place in KSP situations. So when two salts contain the same ion, they're both dissolved in the same solution, the solubility of the salt is decreased because that ion has two sources. That's the common ion effect. So for example, to look at the common ion effect, let's compare the molar solubility of AgI in two sources. One would be pure water, and the other one would be a solution that has NaI in it. So this NaI solution is going to split up because it's a group 1 salt. It's completely to give you Na plus and I minus. And the stoichiometry is 1-to-1 here, so if I have 0.20 molar NaI, I will end up with 0.20 molar I minus in solution. And in the NaI solution, that's going to be on my initial line in my Rice chart. Well, let's get to another space here and solve this problem. So first of all, let's take a look at what's going on in pure water. So we'll have AgI, solid, that we're going to put in the water. It's going to dissociate a little bit and give us Ag plus ions in aqueous solution and I minus in aqueous solution. Initial concentration, don't care about the solid, and Ag and I minus are not present in pure water. Then the change takes place and the stoichiometry is 1-to-1, so that at equilibrium, the concentration of Ag plus is X and the concentration of I minus is also X. Now, we're going to need to find what is KSP for AgI to solve this problem. So KSP is going to be equal to concentration of Ag plus times concentration of I minus, which is going to be equal to X squared. So let's find out the value of KSP by looking on a reference resource. I happen to have a link on our class's Moodle page to a KSP table site on the web, so I'll just open that up and we'll look for silver iodide. So there's silver iodide there, and it looks like 8.52 times 10 to the negative 17th is the KSP value. So we'll put that number in here. 8.52 times 10 to the negative 17th is equal to X squared. So that means that X is going to be equal to the square root of 8.52 times 10 to the minus 17th, and that is equal to 9.23 times 10 to the minus 9th. Well, now let's do the same thing, but for our 0.20 molar NaI solution. So the equilibrium is the same. AgI in equilibrium with Ag plus and I minus. But our initial line is now different. AgI, we don't care about this. There's no silver in solution, but the NaI solution, as we saw, provides us with a 0.20 molar I minus solution initially. So there's a change. And the change is still 1-to-1 stoichiometry, minus X, plus X, and plus X. So that at equilibrium, the Ag plus concentration is going to be X, and the I minus concentration is going to be 0.20 plus X. So KSP, which we know is 8.52 times 10 to the negative 17th, is going to be equal to the Ag plus concentration, which is X, times the I minus concentration, which is now 0.20 minus X. And because 10 to the minus 17th is ridiculously small, it's very reasonable for us to assume that the X in this term can be ignored because it's going to be really small compared with 0.2. So that means 8.52 times 10 to the minus 17th is probably about equal to 0.20 times X. So we can find X by dividing both sides by 0.20, and that gives us 4.26 times 10 to the negative 16th. Now, just for comparison's sake, which is why we did this, look at the solubility of AgI in the I- solution, 10 to the minus 16th, 10 to the minus 9th in pure water. 10 to the minus 16th is 7 orders of magnitude smaller than 10 to the minus 9th. 7 orders of magnitude is 10 million. So 10 million times less silver iodide will dissolve in the NaI solution than would dissolve in pure water, and that's the common ion effect. One of the real common applications of KSP is using it to determine if a precipitate is going to form if you put together two solutions that have ions that have the potential to precipitate. So here's how you do it. The first thing you want to do is find the actual value of the ion product, Q. Now remember Q, we haven't worked with this for a while, but Q is pretty much the same as KSP, except for it's under actual conditions, not at equilibrium necessarily. And then you use Le Chatelier's principle to predict will a precipitate form or will a precipitate not form. So here's the thinking. Imagine that you have your generic cation salt, and it dissociates and it gives you aqueous cat ions and aqueous N1- ions. KSP here is equal to the concentration of the cation at equilibrium times the concentration of the anion at equilibrium. Q is equal to the concentration of the cation actually times the concentration of the anion actually. Now, if Q ends up being larger than KSP, that means that my reaction is going to want to shift to the left. If it does that, it's going to reduce the concentrations of both cation and anion, and Q will get back closer to KSP. Well, shifting to the left means that more of the solid is going to form. So if Q is bigger than KSP, our conclusion is going to be, yes, a precipitate will form. Now let's look at the other situation. If Q is less than KSP, what does that mean? Well, if Q is less than KSP, then that means the concentrations of cation and anion are not large enough. So the system is going to shift to the right in order to make these concentrations rise so that they can get up high enough to be equal to KSP. So if Q is less than KSP, we're not going to get any of the solid that's on the left-hand side, and the precipitate will not form. So we can use this set of rules here as a guideline to solve these kinds of problems. So here's a problem to solve using this technique. Will a precipitate form if 100 milliliters of a 1 times 10 to the minus third molar lead nitrate solution and 100 milliliters of a 2 times 10 to the minus third molar magnesium sulfate solution are mixed? So this is the situation. We've got one beaker. I'm going to call this beaker number 1. And then we're going to have a second beaker that has our other solution in it. And this will be beaker number 2. And we're going to pour these together into a third container. And this will be beaker number 3. So what do we have here? In beaker number 1, we have 100.0 milliliters of a 1.0 times 10 to the negative third molar solution of lead 2 nitrate. In beaker number 2, we have 100 milliliters of a 2.0 times 10 to the minus third molar solution of magnesium sulfate. In beaker number 3, well, we're going to have all of these ions together. We are going to have in here Pb2 pluses from beaker number 1. We're going to have nitrate ions from beaker number 1. We're going to have magnesium ions from beaker number 2, and we're going to have sulfate ions from beaker number 2. And the other thing that we know here is that the total volume of beaker number 3 is going to be 100 milliliters plus another 100 milliliters, so 200 milliliters. Now, if any precipitate forms, what is it going to be? Thinking about the combinations that we could put together here, if I put lead together with sulfate, that's a potential precipitate because sulfate has limited solubility with lead. So we could have this equilibrium get established here, PbSO4 solid, in equilibrium with the Pb2 plus ions and the sulfate ions that are present in solution. The other combination is magnesium together with nitrate. Well, nitrate salts are all soluble, solubility rules say. And so it's very unlikely that a precipitate is going to form between these two. So we're not going to bother worrying about magnesium ions or nitrate ions. So what we need to know here is what is the Q for this reaction, and then compare that with the KSP for that reaction. Well, let's go find out what KSP is. We're now looking for lead sulfate. Lead 2 sulfate has a 2.53 times 10 to the minus 8th value for KSP. So let's record that, 2.53 times 10 to the minus 8th. So if Q is bigger than that, we'll get a precipitate. If Q is smaller than that, we won't. Let's find out what Q is. Well, Q is going to be the concentration of Pb2 plus actual times the concentration of SO4 2 minus actual. So we have to find out what those concentrations really are in beaker number 3. Well, from beaker number 1, we get this, 100.0 milliliters times the concentration, 1.0 times 10 to the negative third moles of PbNO3 2 per liter. And then what we're interested in is the lead 2 concentration. And if you think about what happens in that beaker, it's PbNO3 2 completely dissociating, because nitrate salts are soluble, to Pb2 plus 2 NO3 minuses. So the 1-to-1 stoichiometry tells us that every 1 mole of PbNO3 2 that's dissolved in there is going to give us 1 mole of Pb2 plus ions. So you work this all out, and here's what you find. 0.100 millimoles of lead 2 ions are present in that first beaker, and so that's how many are present in the third beaker. Now our sulfate comes from beaker number 2. What do we have there? Well, again, we have 100 milliliters, but the concentration is different. We have 2.0 times 10 to the negative third moles of magnesium sulfate per liter. And every 1 mole of magnesium sulfate is going to provide us with 1 mole of sulfate ions, because the stoichiometry is going to be 1-to-1 there too. Think about MgSO4 solid completely splitting up to give us Mg2 pluses and SO4 2 minuses. We know this is highly soluble from our solubility rules. And this is balanced the way it is, so this is a 1-to-1 combination. So when you work this math out, you get 0.200 millimoles of sulfate are present in beaker number 3. So what is Q? Well, our concentration of lead 2 in beaker number 3 is going to be the 0.100 millimoles that were poured in there from beaker number 1 divided by the total volume of 200 milliliters. The concentration of sulfate is going to be the 0.200 millimoles of sulfate that were poured in from beaker number 2 divided by the total volume in beaker 3, which is 200 milliliters. Both of these are raised to the 1 power because that's the stoichiometry of lead sulfate's equilibrium. And when you work this out, you get 0.0015. Well, that's our value of Q. It is much larger than our value of KSP. So therefore, we can conclude that a precipitate will form in this reaction. I'm going to finish this up with a kind of a practical example of the power of KSP in determining real-life situations like tooth decay. Normal tooth enamel is made of a mineral called hydroxyapatite. And hydroxyapatite has this formula. It's got 1 cation but 2 anions. When hydroxyapatite is exposed to water, like your spit, for example, the solid is going to split up reversibly and give you 5 calcium ions and 3 phosphate ions and a hydroxide ion, and these are all going to be in aqueous solution. So on the left-hand side, you have solid tooth enamel, and a little bit of it dissolves. How much? Well, a really little amount. KSP here is equal to 6.8 times 10 to the negative 37th. So that's not very much, which is good because otherwise your teeth would dissolve in your spit. But it is something. And so very, very slowly your tooth enamel can decay. It's so slow that in normal spit, teeth would last, well longer than a lifetime probably. Now here's a problem that many of us have. When you eat sugar, some of the sugar remains in your mouth. It's stuck to your teeth. It's dissolved in your spit for a while before it all gets flushed out of there, and so it's there. And it's a food source for bacteria. And then so there are some bacteria that consume this sugar, respirate it, and when they respirate it, they don't produce CO2 and H2O like we do. They will produce acids as a byproduct. So who cares if they produce acids? Well, remember this equilibrium? Think about what happens if you introduce a bunch of H+ ions into your mouth. And you can do this by either the sugar bacteria thing that I was just talking about, or just plain, eating or drinking a lot of sour foods. OH- plus H+ is going to give you water. And the K for this reaction is very high. It's 1 over kW, so it's 10 to the 14th. That's a very large number. And so that means this reaction is virtually a one-way reaction. So that means every H+ that you introduce into your spit neutralizes and removes from your spit an OH-. Well, if I take OH- and take it out of the system by reacting it, what happens to the equilibrium? According to Le Chatelier's principle, that's going to cause an equilibrium shift to the right. So that means more tooth enamel, more solid, is going to dissolve in your mouth if you put acid in your mouth, or if you put enough sugar in your mouth that the bacteria create the acid for you. So that's how you can make tooth decay go faster. Eat acid or eat sugar. In about the early 1960s, a dentist figured out that putting fluoride ions into your body changes your enamel to another mineral. It's no longer hydroxyapatite. It's something called fluorapatite. And this is the reaction that causes that to happen. Fluoride ions that will be in your body will replace the hydroxide ions and give you this new mineral. This is the fluorapatite, and loose hydroxide ions. Well, fluorapatite is also going to dissolve in water. So I have my Ca5PO4,3F solid, and it dissociates to give you 5 calcium ions and 3 phosphate ions and an F-. But KSP for this reaction is 1 times 10 to the negative 60th. For the hydroxyapatite, it was 10 to the negative 37th. Well, this KSP, 10 to the negative 60th, is more than 1 billion times smaller than the KSP for hydroxyapatite. So normal tooth enamel dissolves 1 billion times better than fluorided tooth enamel. So that means that our tooth enamel is much more likely to stick around and not dissolve if it's this new kind of artificial enamel that's created by plenty of fluoride being in our diet. Here's another reason that fluorided teeth are better. In hydroxyapatite, the H+ was reacting with OH- that was in your spit from the hydroxyapatite, and it was virtually a one-way reaction to produce H2O. K for this reaction, remember, was 10 to the positive 14th, which is a very large number. Now, if H+ is introduced into a mouth that has fluorapatite enamel, the reaction here is more of a reversible reaction because F- is a weak base, and so you're going to get HF produced not quite as strongly. Now, K here turns out to be 1 over the Ka for HF, and Ka for HF is 3.5 times 10 to the minus fourth. So this is still a big number. It's like 2,900. But 2,900 is about 100 billion times smaller than 10 to the 14th. And so less F minus will be removed from your spit. And so the Le Chatelier shift to the right that decays your tooth enamel will be not as extensive if the enamel is fluoroapatite rather than hydroxyapatite. So adding fluoride to your body reduces tooth decay. Adding sugar and acid to your mouth increases tooth decay. And it's all about KSPs.